Hey, how's everybody doing? Welcome back to Math for Healthcare. Here we are starting our next module, and that's going to be probability distributions and random variables. And both those things are really so we could get to slightly more complicated probability problems and ideas. And what it starts with is learning how to find counting the size of things, or finding the size of sets, and the size of events, and the size of sample spaces. Why is this report important? Well, recall in our previous module, right, we had to restrict ourselves to a finite and uniform sample space. For instance, when we're tossing two coins, right, our sample space, heads, tails, tails, heads, tails, tails. Why? Because those are equally likely outcomes, and when we have that and it's finite, we know that we could find the probability of an event E is equal to the size of that event over the size of the sample space. So now we need ways to count the size of these events or sets, right? Both the sample space and the event, in more complicated cases than we've seen so far. And why is this? Well, when things get large, it gets difficult. For instance, well, what about when you're tossing 10 coins? You don't want to list all that out, right? All right, so let's see what we could do here and to get started. First of all, let's consider finding the size of the sample space in an experiment where we roll a three-sided die and then flip a coin. Right, so three-sided die can have anything on the sides, but let's say it's 1, 2, and 3. Okay. Now this one we can actually write out the whole sample space and do it similar to the coin one. But let's see what happens. How we want to be able to do this in general when we have bigger things than this. But we start with something like this. Now, one way to see this is, well, just like with the coins and the conditional probabilities, we're going to draw a tree diagram. Right? So here, we could either get a 1, a 2, or a 3, right? And then the next thing to happen is flipping a coin, which could be a heads or tails. Heads or tails. Heads or tails. Okay? And notice, what do we have? We have the first event, not the first event. We have the first process here is we're tossing a coin, and by first, that's just labeling it that way. All right? And this is flipping our die and then tossing our coin. All right? Now, what do we see here? In the end is, well, down, let's say this path here, all right, what's that, the event? We think of that as 1H, and by the way, that means that would be something in our sample space. So, our sample space here does equal, it's got 1H in it. What else does it have? Let's see, the green path, say 2, and then T, that's saying rolling a 2 and then getting a tails, and that would also be an element. If we do it this way, we get equally likely events, and we want to find a way to count the size of this. So hopefully you see it from drawing out this chart that we get how many? 6. 1 for each leaf at the end of the tree. And that's 6 of them. Now, what is this really using? Notice, how can we do this in general? Well, let's say, oh, I see. So let's say I came over here to 1, then for each of the 1, 2, and 3, I could get a heads or tails. That for each is telling me there's going to be, for each, that 1, 2, and 3, there's going to be 2 leaves coming out from that. And that for each tells me it's multiplication. And there's 3 ways to toss the die and 2 ways to toss the coin, and we multiply those together to get our sample space size, which is 6. And this is the basic multiplication principle. Right? Suppose there are m ways now. Before there was 3, but now it's in general. When there's m ways performing task 1 or to make choice 1, and n ways of performing task 2 or to make choice 2, then there are m times n ways of performing task 1 followed by task 2 to make the choice 1 and then choice 2. Another way to say it, right? So this multiplication principle, almost all our counting is going to be based on using this multiplication principle. It's fairly important. It's getting to the idea that for each one of the first things, there's this many in the second, right? And notice here what this is going to do is it enables us to find probabilities without listing everything out. Because I know you guys weren't fond of listing out, even 3 coins, right? The size of that sample space was 8. That's a lot of things to write out each time. All right, now let's consider what if we were finding the size of the sample space in an experiment where we roll 3-sided die and then flip 2 coins. Okay, so now I could draw another tree diagram, but it's going to kind of get messy. Let's use the multiplication principle that we learned. So let's see here. What do we get? We have a 3-sided die. So there's 3 possibilities for that die. Let's say coin 1, there's 2 possibilities for coin 1, and coin 2, there's 2 possibilities. And what do? We use our multiplication principle. But here you say, well, it's a little different. Now I'm doing, if I did the multiplication principle before, we have 3 things, not just 2 things, right? And so it's 3 times 2 times 2. Which hopefully that makes sense. That's for each of the 3 die outcomes. For each of the 3 die outcomes, there's 2 coin outcomes, and so it's that multiplication, that for each. And then for each of those 6 possible outcomes, there's another 2 for each of those, right? You can imagine at the end of our tree diagram from last slide is that would just be another 2 coming out from each one of those leaves, 6 leaves that was already there. And here we get the generalized multiplication principle. This notation, these dashes, I think are very helpful for doing your probability problems. You should be writing those down when you're doing the problems, okay? So here, what do we get? What's the size of the sample space? Let's get back to blue. What's the size of the sample space? 3 times 2 times 2 gives me, of course, 12. And so now we know that there's that size of that sample space is 12. We don't have to list them all out. Now, maybe just as a reminder, what some of those will look like would be a 1, a heads, and then a tails. Say a 2, heads, and a heads. And there's a whole bunch of, there's 12 of those in there. I'm not going to write them all out, but that's what we're doing. All right? So let's do some. What we use there, we used it for 3. In general, we could use the generalized multiplication principle, okay? And if we have n choices that we make, and there's m1 ways to make choice 1, m2 ways to make choice 2, and so on up to mn ways to make choice n, then what do? The sequence of all those things together, or all those choices together, is going to give me the product. How many are there? The product of m1 times m2 all the way through mn. So in this case, with the 3-sided die and flipping 2 coins, you could say m1 equals 3, m2 equals 2, and m2 equals 2. And we multiplied those all together. Okay, and really over here, I kind of think of it as when we do these and this is choice 1, choice 2, choice n, and so on. And choice is, choice or task, whatever it is. let's look at an example. How many 6-character license plates are there where the first 3 characters are letters and the second 3 are numbers? All right. What are our data? I want you to think about it. Okay, what do we got here? 6-character license plates. That's 6 tasks, or 6 tasks, or 6 choices. All right, and so let's see here. We have what? First 3 characters are letters. So I'll say letter 1, letter 2, letter 3, and then we have 3 numbers. Okay. Number 1, number 2, number 3. Now, note that when we say numbers, okay, they're talking about single-digit numbers. So the numbers possible are 0 to 9. Those are the digits, so there's 10 of them. Okay? Now, can you check that? Remember, counting on your fingers is okay. I know plenty of PhD mathematicians that use their fingers to count, because you got to double check. This is a little funny. You see it 9, you think maybe there's only 9 of them, but you check. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. With that 0 is that there's actually 10 options. So so we got 10 options for the numbers. So let's see here. How many letters do we have? We don't know how many letters in the English alphabet. There are 26. You can look that up if you need to. So 26 for the second, 26 for the third, and then 10 for each number. And we get 26 cubed times 10 cubed. And in GeoGebra, I'm just plugging that in. Nothing fancy here. It's okay if you can't see in my GeoGebra window too well right now. I'm not doing anything important. Times 10 cubed. But you should get used to doing this. It's good to see these big numbers that we're going to get an understanding of them. So this is about 17.5 million, right? And just as a reminder in scientific notation, we'd write this as, say, 1.76, say, rounded, times 10 to the, what we got there, 6, 7, right? 7. Good. Let me know if you have any questions on these. Don't forget to just send me an email if you are missing something. But it's good to practice as well. Okay, let's try one more. Let's try another example here. Now we got a bike lock requires 4 digits. Here we distinctly say 0 to 9 to be selected in order. What's the probability of guessing a combination? All right, well, what do we got? We got 4 digits. Okay, so that's 4 of those. Each one of those is a digit. Let's call it, I'm going to call it digit 1, digit 2, digit 3, digit 4. And so here we get 10, 10, 10, and 10. Okay. Now, so here, this is the number. So since it's asking for a probability of guessing the combination, okay, so let's think about that. So that means what we just said is the size of our sample space in this problem is 10 to the 4th, okay, which is 10,000. All right, well, if you have no idea and you're guessing, there's only one correct guess, or one correct combination, and so that's going to be 1 over 10 to the 4th, right? There's only one correct one. That's the size of the event. That's the numerator. Our denominator is the size of the sample space, which is 10 to the 4th here. Okay. And just so you know, you could write this as 10 to the negative 4th. Again, a reminder. Good. Okay. Let's see. Find the probability of all heads if you flip 10 coins. Right. So here, and just like other problems, just like in the last module, we really want to find the size of the sample space first. That's That's always your starting point. So here, what? We want the number of ways to flip 10 coins. And I'm going to have a dash for each 10 coin. I'm not gonna, each of the 10 coins. I'm not going to draw all those. How many possibilities for each? There's 2. Right? Okay, heads or tails. Each coin's heads or tails. So that we use our multiplication principle here. That gives me 2 to the 10th. All right, just to give you an idea of what that number is, I'll plug it in real quick. Again, I think it's good for you to do too. 2 to the 10th is 1,024. Right? Not that big, but you certainly don't want to write all those out. Now, how many ways can you get all heads? All right, so the size of our event really is what we're asking there. Where E is the event, we get all heads when tossing the coin. Right? All heads. So what's the size of our event here? It is just 1. And so the probability of E, which is all heads, right? All heads when tossing 10 coins, that's going to give me 1 over 2 to the 10th, which is, one way is write that as 2 to the negative 10th, and you could estimate that to be about, let's see here, it's going to be about 1/1000th, right? But might as well plug it in. We got it there, and we get 0.00098, and I am doing a real rounding, and remind you that we could take advantage of our scientific notation to write that as 9.8 times 10 to the negative 4, correct? Yeah, -4. Good. All right. Oh, keep on forgetting that that's not the way that works. All right, so each office at FVCC has a phone, and all the numbers start with 406-756. How many different phone numbers could the college have? What if the first digit cannot be 1 or 0? So notice this isn't a probability problem. This is just counting the number of things here, right? And you have to be careful. You got to pay attention to that. Sometimes they'll just can't ask you to count the size of it, and in other times they'll just say they'll ask for the probability. Here, basically, we could think of this as counting the number of 4 digits, any 4 digits. So really, again, we got 4 different digits, and there's 10 possibilities for each. So if there's no restrictions, what do we get? 10 to the 4th. Again, that's 10,000 phone numbers. Okay. Now, what about the second part? What if? Let's concentrate on that now. Maybe I'll do it in a different color to separate it here. So what if the first digit cannot be a 1 or 0? How does that change things? Well, certainly we still have the 4 dashes, right? Okay. Now, okay, so the first digit, so there's 8 possibilities for the first digit, right? Because it can't be a 0 and 1. Now, the second could be anything, the third can be anything, the fourth can be anything. And that's going to give me 8 times 10 cubed, which is 8,000 phone numbers. Right? Good. Now, what do we got here? And how about a combination lock that requires 3 numbers from 0 to 39? So this is more like you turn it kind of thing. But you can have the same number twice in the row. How many different combinations are possible? All right. Again, this is asking for a number, not a probability. But really, that number is, what are we finding? The number of ways, it's the set of all different possible lot combinations. Right? That's really what we're counting. All right, so 3 numbers. So we got 3 dashes, yeah. And let's see, 0 to 39. How many are there? Be careful. Here you don't want to go all the way up to 39. So what I do is check. Oh, what if it said 0 to 4? Then it would be 0, 1, 2, 3, 4. So that's 5 possibilities. So if it's 0 to 39, there must be 40 possibilities for the first number because it's unrestricted. Now, we can't use the same number twice in a row. So how many do we have for the second number? Good, 39. All right. Now, how about for the third number? Well, the third number can't be the second number, but it could be the first number, so we still got 39 left. And so we multiply those 3 together using our multiplication principle. And we end up with, again, I'm just doing a basic calculation here. You don't really need to see my screen for this. Looks like it comes out to be 60,840. Okay? So notice that's quite a bit bigger than, remember when we just had 3 that were 10? Even the 4 that were 10. You know, 3, but 3, if we only had digits, that would be 1,000. This is growing quite big. Okay. How about we got a teacher that has 5 different books that she wishes to arrange side by side? How many different possible arrangements are there? Again, we're saying, what is the size of the set of all arrangements of these 5 books? All right, so let's see. A couple things. First of all, let's imagine what they're talking about. Sometimes it's good to write down. Let's say we have a math book, a biology book, a chemistry book, a physics book, and an econ book, okay? So this would represent one arrangement, right? The math book, then the biology, and then the chemistry, and then the physics, and then the econ. What would be another thing is, say, well, we could still start with the math, but maybe chemistry first, and then physics, and then biology, and then that would be another arrangement. And we want to count all those, okay? And we want to use our multiplication principle. So we have 5 books, 5 slots really, right? Where does a book go? This is basically the first, let's say, position 1, position 2. So for instance, in this example here, the math book is in position 1. Okay, so what do we get here? For position 1, how many possible books do we have? We have 5, right? Any one of those 5 books could be in the first position. The second position, well, now we have how many books? Well, we can't use the math book again. We only have 1 math book, right? So now we only have 4 possibilities. And then 3, and then 2, and then 1. And we multiply those all together, 5 times 4 times 3 times 2 times 1. Okay, and this gives me, what does that give me? 20 times, I better do it in my calculator. Now, 120, okay? Now, if you could see in my Desmo screen, and it's not necessary, I entered 5 exclamation point. That means 5 factorial. And I'll be putting it on the next slide. This is very useful notation that we'll be using, and I'd like you to get used to. 5 factorial. All right, so we want to count the number of ordered lists of distinct objects. Yeah, n distinct objects. So up top we have 5 distinctly different books. Okay, the number of such lists is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. So it's the multiplication principle. And so for convenience, we write that as n factorial, right? And notice our 5, right? That's 5 times, up in this case, 5 factorial was 5 times 4 times 3 times 2 times 1. So, an n factorial counts the number of ordered lists of n distinct objects. What this means is 0 factorial equals 1, since there's only one ordered list with no objects. This is the empty list or the empty set. That's the real reason behind it. If you don't like it so much, just know that, just memorize that 0 factorial equals 1. It's rare that we use that. Okay? More important, the factorial notation and what it counts, the number of ordered lists of n distinct objects. So for instance, let's say on this one above, and I am instead doing the problem where a teacher has 15 books. How many different possible arrangements? Well, it's 15 times 14 times 13, but we don't want to write all that out. We know we're advanced enough to say that's 15 factorial, and we could plug that in. Again, just 1, 5, exclamation point, and that turns out to be about 1.31 times 10 to the 12. Very large number, right? Bigger than a billion. Bigger than a billion by a bit. What is it? Almost a trillion or something? Or about a trillion? Anyway, you should think about those numbers and how big. The idea here being is notice 5 factorial is only 120, 15 factorial is 10 to the 12. Factorials grow extremely large, quickly. Suppose we have 10 people applying for a job. How many ways can we order those candidates from most desirable to least if there could be no tie? Okay, yeah, and we want to think about, you got to picture this problem. It is a multiplication principle. Well, from order the candidates from most desirable to least. We could only have one top spot, that's 10. The second slot now, since we already have the first one, is going to be 9, 8, and that's going to continue on for 10 of them. And hopefully we see that's going to be 10 factorial orderings. You could think of those 10 people as 10 different letters, 10 distinct letters, and how many ways can we arrange them, right? It's really the same problem. That's always important in this class when you see the similarities between problems, even though the units may be different. And just for to do, we get, let's see, 10 factorial is approximately 3.6 million. Okay. Good. So that's if we are ordering them all. Now, what happens sometimes is, maybe we only want to do our, what if we just want to order the top 3 candidates? How many ways can we do this? All right, well now, we only have 3 candidates to order. But how many possible are for the 10 candidates? Or for the first one, there's 10 candidates for the first position, right? Still just like before. And there's 9 candidates for the second. And then there's 8 candidates for the third. However, let's be clear, position 1, position 2, and position 3. That's it. We don't care about the rest of them. And so here we use our multiplication principle, and we get 10 times 9 times 8, and this turns out to be and it's important that we distinguish between the two, and this is 720. Now, in the next video, which we're not quite ready to go to yet, we will learn how to do notation for this kind of, this is also a kind of permutation or arrangement, right? And we'll learn some notation so we can plug it into Desmos with bigger numbers, but for now, just it's important to see the difference between a full factorial and using the multiplication principle just on the first three in this case. Now, so far, we've only considered when we have distinct objects, right? Now, there's a lot of situations where we want to find the permutation set of objects. Not all objects are distinct. For instance, how many ways do they rearrange the letter of the word dad? Here, D and D, they're not distinct. We can't tell the difference. Okay, so to give you an idea of how we count all of them, first, let's pretend like the D's are different colors. All right, and so they're different things. So we have three distinct objects. What's it going to be? There's going to be 3 factorial, which is 6, if D's different colors. All right, and I'll list all those out here. Let's say color 1 and color 2 because then I can change colors each time. We have D1, A, D2. That's one arrangement that we counted. Then we have D2, A, D1. That's another arrangement that we have. We have D1, D2, and A. We have D2, D1, and A. Over here, let's see, what else do we have? A, D1, D2, A, D2, D1. Oh, and that's 6. All right, there's our 6 of them that we have. Now, what about when they are not? Remember, that's the 6 if they're distinct. But now, what happens when we erase, if I erase or hide the 1s and 2s, so to speak? Well, what happens is these two then are the same thing. They don't count as different things. These two are the same things. They don't count as different things. These two are the same things. They don't count as different things. So when we don't have distinct objects here, if not distinct, then we have how many? There's 3. All right? How am I getting this? This is going to be, in general, when you move, you don't have to do this every time. This is explaining where our formula comes from, which will be on the next slide. In this case, this is saying, well, we have 3 factorial total, and then for each one of those ones, there's a double up, or divided by, it's 2 factorial. That 2 is really coming from, we have 2 D's that are the same. And so this, of course, comes out to be 3. And in all its glory, well, maybe before we do the general, we'll do one more. Let's say we rearrange the letters in the word mama. Okay, so now we have, let's see, 1, 2, 3, 4, 5 total. Okay, so if they were all distinct, you'd have 5 factorial things. However, what? We got to divide by the number of orderings of the m's. So there's 3 of those m's. We divide by the 3 factorial, and this turns out to be 20. Don't worry about how I do that quickly. Well, it's actually pretty easy, right? 5 factorial is 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. So it's just going to cancel off and we get this. All right, and so we get 20 distinct rearrangements when we don't have all distinct items. And in general, what does it look like if we have a string of n characters, k of which are distinct? The number of distinct rearrangements of all n characters, n factorial over n1 factorial times n2 factorial, and so on, where n1 is the number of repetitions of the first k characters, t2 is the number of repetitions of the second of the k characters, and so on. So for instance, in Mississippi, what do we got there? I think it's 11, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's 11 factorial. And let's see, we only have one m, so technically you could write down 1 factorial, but dividing by 1 doesn't do anything, so I'm not worried about that. Let's see, 2, let's see, we got 1, 2, 3, 4 i's, so that's going to be divided by 4 factorial. And then we have 4 s's, so times 4 factorial in the denominator there. And then 2 p's, so it's 2 factorial. This one I can't do in my head. And we end up with 11 factorial divided by looks like we end up with 34,650. And just to give you an idea, if all those were distinct, it'd be 11 factorial arrangements, and that's 11. That looks pretty close to about 40 million, just so you know how that changes things. So big difference. Okay, so that's important. We got to be able to see the difference between when things are distinct and when they are not. All right? And let's do one more example. Student buys 3 cherry yogurts, 2 raspberry yogurts, and 2 blackberry yogurts. Puts her in the refrigerator, eat one for the next week. How many ways can she select yogurts to eat for the next week? So this may be hard to see, but this turns out to be, this is exactly what we've just been doing. We could think of it as, the question as, how many ways are there to rearrange the letters C, 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 right? We'll use that for cherry yogurts. R, R, B, B. Whereas, for instance, this arrangement would represent me eating 3 cherry yogurts the first day, then, cherry yogurt each of the first 3 days, raspberry yogurt each of the 3rd and 4th day, and then blackberry yogurt's the last day. And we want to know how many ways can we rearrange those things. It's just like counting the letters in Mississippi. We have, what, a total of 7, so it's 7 factorial over 3 factorial, because there's 3 C's, times 2 factorial, because there's 2 R's, times 2 factorial, because E's. And just to completeness, to get that number, we get what? What is that coming out there? I'm in trouble with this one for some reason. 210 ways. 210 different ways for her to do that. But there, again, see, the calculation is not the hard part. It's seeing that this is basically the same problem as Mississippi. Obviously not the same numbers, but you're using the same process. Okay, and hopefully that makes sense. You should go ahead and do some homework of problems. And please let me know if you have any questions. That's really going to be helpful. All right, I'll see you next video.